So let's remember where this 2 came from. We're going all the way back to the second week of class now. We had the empirical rule, the 68, 95, 99.7% rule, also known as the empirical rule. And at that time, we learned that 95% of the time, if we have normally distributed data, and P-hat will be normally distributed here, if we normally distributed data, 95% of the time we get a z-score between -2 and +2. And we're going to learn in a little while that it's not quite precisely -2 and +2. In fact, I'm going to try to tweak that and make it a little bit better right now. So we're going to learn how to get this number. At least we're going to learn a couple different ways of getting this number. All right. One way is to use our z-table backwards. If I want this area to be 95%, which is 0.95, then I've got 0.475 here and 0.475 here. Half of 95%. Also, if I've got 95% in the middle, and those 2's are not quite correct anymore, if I've got 95% in the middle, I've got 5% being shared between these 2 tails, which means I've got 2.5% in that tail. Is the orange showing up okay? I've got 2.5% in this tail and 2.5% in this tail. Note that these 2 add up to 0.5, 0.5, and all 4 of these add up to 1. Got 95% split between these 2. The other 5% is out in the tails, cutting that in half. 2.5% in this tail, 2.5% in this tail. What I want then is the z-score that makes this area 0.475 and this area 0.025. So hopefully, as I asked, you have the z-table printed out and sitting right next to you as you're doing this. What we want to do is we want this area ideally to be 0.475, and if I get ridiculous on the decimal points, 0.47500. Remember how your z-table is built. I don't need a close-up on it here. But let's remember how your z-table is built on the outside. That is the far column. I'm going to leave it. It's not all that important. This column and the top rows, these make z-scores. And the body of the table is areas. So I want to scan the body of the table, those 5-digit decimals. I'm going to scan the table. I want the area to be 0.475. Okay. So again, we're using the z-table backwards, trying to make the area 0.475. So scan the z-table backwards. This time we're going to get lucky. 0.47500 is on my table. If it isn't, I get as close as I can. But if I want this area to be 0.47500, what I'm going to find is that this z-score is 1.96. And down here, negative 1.96. Okay. So to get this critical z-score here, again, I could use the z-table backwards to get negative 1.96 by symmetry. On the other side, negative 1.96. That makes this area 0.475. That makes this total area here 0.95. So to be a little bit more precise here, I should make my E not 2 times the standard deviation, but 1.96 times the standard deviation. And my error is not going to be 0.0326. I should say my maximum likely error estimate, but is going to be just a little bit narrower. I'm going to call it 0.0319. So not much of a difference, but to be a little bit more precise, this should be 0.0319. I get a slightly narrower interval of 0.695 plus or minus 0.0319, which is 0.6631 to 0.7269. Okay. A couple of ways this might be reported to us. They might report that after our experiment, the way it's usually reported in the news, they don't talk about 95% confidence intervals, but what they'll say is that our experimental data shows that the thumbtacks land safe 69.5% of the time, and then the broadcaster will mumble something about the survey had a margin of error of plus or minus 3.2%. And when you hear that, when they're reporting survey results, that the survey had a margin of error of plus or minus 3.2% or whatever they say, they're usually giving you what is the error for a 95% confidence interval. Okay. Now let's suppose instead we want a 98% confidence interval. For P. Well, I'm going to introduce some new notation here along the way. Okay. Alpha is used a lot in statistics to represent the probability of being wrong. And for a 98% confidence interval, alpha is 2%, which is 0.02. Now remember that 2% is going to be shared between the two tails. I'm going to use a different z-score instead of 2 or 1.96. In order to gain confidence, I'm going to use a bigger z-score. And what I'm trying to do now is find that z-score. So if I've got a 98% confidence interval, half of 98% is 0.49. And hey, your z-table goes 5 decimal places, so you would hope to find 0.49000 on there, but you won't. Okay. Now, we'll have a little less area in the tails here. If I've got 98% in the middle, I've got 2% in each tail. So I'm going to come out a little bit further so that the area in each tail now, instead of being 2.5 or 2.5%, now it's only going to be 1% or 0.01. Okay. So 98% in the middle here between two z-scores that I've got to find. Okay. 1% in each tail. Okay. And the amount in each tail, the area in each tail, is alpha over 2, which is 0.02 over 2, which is 0.01. So, again, alpha is the probability of being wrong. If I've got a 98% confidence interval, 2% chance of being wrong, wrote that as a decimal. How much is in each tail? I take this 2%, I divide it by 2 to tell me what the area in each tail is going to be, which is 1% or 0.01. Now, some new notation still. Z with the subscript 0.01 is the z-score leaving 0.01 in each tail. So scan your Z table backwards and you're looking for 0.49000. So scan the body of your Z table again, looking for 0.49000. I'll give you a moment to do that while I'm erasing the board. And to your frustration, you are not going to find in your table 0.49000. You can figure out about where it would be, but you're not going to find it exactly. So what I am seeing on my table is that if Z is 2.32, the probability of seeing a z-score between here and 2.32 is 0.4983. And I'm leaving a little space here. At 2.33, I get 0.49010. So what is the z-score that leaves 1% in each tail? I don't know precisely from my z-table, but I know that it's somewhere between 2.32 and 2.33. And when you're making your confidence interval, what do I multiply the standard deviation by? Not 1.96 anymore. I'm not going to punish you if you use 2.32 or 2.33. It's somewhere in between. And some books say always round up to be a little bit bigger because it's better to make your confidence interval a little bit too wide. If we're advertising it as a 98% confidence interval, I'd rather be a little more than 98% confident instead of a little bit less. All right. Now, if I want more precision on this, there's a couple of ways to go. One thing that I haven't shown you yet is the t-table. We've got a picture of the t-table here, and we're going to ignore most of the t-table. Okay. All we're going to really use is the top line and the bottom line. Now the bottom line, where it has the infinity and it's in bold, those are z-scores. The top line is the area, but they don't give us the area in the tail. They give us the area to the left. The column that we're going to use is not 0.98, but 0.99. Because the area to the left of this mark is 1 minus 1%. Or it's got this 98% plus this tail on the left. So the column is 0.99. And if you follow the column for 0.99 and go all the way down, you'll see at the bottom 2.326, which is between 2.32 and 2.33. The other way to get this number is using your calculator. If you ask your calculator for inverse normal 0.01, you're asking your calculator, hey calculator, find me the z-score that leaves 1% in the lower tail. And the calculator, if you go to distributions and choice number 3, inverse normal of 0.01, my calculator tells me to ridiculous accuracy, negative 2.326347877. Now that's way overkill on the digits. All right. But what I wanted to demonstrate to you here is that we've got 3 different ways to find this critical z-score here. Okay. One was to use the z-table. I want this area to be 49%. Looking for 0.49000 in the body of my table. I don't have it, but I know it's between 2.32 and 2.33. Okay. Using the t-table, 2.326 gets me a lot closer. To a ridiculous number of decimal points. We'll get to 0.49. All right. But again, we don't need to go that ridiculous. So you got 3 tools to do this: the z-table, the t-table. But remember again, for a 98% confidence interval, the area that I'm looking up is 0.99, or inverse normal. Now, inverse normal told me that negative 2.326 is the z-score that leaves 1% in the left tail. By symmetry, I know that positive 2.326 leaves 1% in the right tail. If you wanted to have your calculator spit that out, it's inverse normal, and the common mistake people make is to put 0.98 here. It's not. We want 0.99, even though we're making a 98% confidence interval, because the area to the left of this mark is the 98% plus this one tail. All right. So now, my error is going to be, here's the formula. In general, z with a subscript of alpha over 2. What's alpha over 2 in this case? It's 0.01. That's new notation to you, and it means what's the z-score that leaves 1% in each tail. And we found that 3 different ways. I'm going to call it 2.326. Again, I wouldn't beat you up if you used 2.32 or 2.33 there, times S of p hat, which is still 0.016278. And I am going to get 3 point, or 0.0379 if I round it to 4 decimal places. At this point, you want the same number of decimal places you had, maybe one more. So my error is going to be 0.0379. And then my confidence interval, making a 98% confidence interval for P. Same P hat, but now my E is 0.0379. And my confidence interval is 0.6571 to 0.7329. Okay, that's a wider confidence interval than I had before. Why is it wider? Because I'm more sure it's correct. I'm now 98% confident that my interval is correct. Okay. Mac assignment 32 was dedicated to helping you find these critical z-scores. Tried to walk you through that slowly, but Mac 32 dedicated to helping you find those critical z-scores. And then Mac 34 actually has you doing a full example.